Glad YouTube is starting now and not 5 minutes ago, but that's okay. Yeah, we're not going to say purple drink anymore, for the record. For the record, we're not saying purple drink anymore. So let's try this one time. On the assignment yesterday, some of you were getting irritated at me. Some of you were getting irritated at me because you could only really do, we finished half the unit, but you could only really do maybe a third of the questions or a quarter of the questions, because some of the questions had this thing where it was identify the oxidizing agent, or identify the reducing agent. Now, the reducing agent, please do not get that mixed up with something that's being reduced. They're actually totally opposite of each other. For example, I'll just write, we'll just talk about here. We'll just talk about this reaction here. Nope, that's what I want. There we go. So the reaction at the bottom here, what's being oxidized and what's being reduced?
Zinc is being oxidized.
Zinc, this thing is being oxidized. How do you know it's being oxidized? It's losing electrons because it's becoming more positive, right? If its oxidation number is increasing, that's being oxidized, right? If its oxidation number is decreased, then it's being reduced. Okay, so that means the copper 2+ ions, that's being reduced. Now, what is causing, I'm curious, what's causing zinc to be oxidized? What is the substance that's causing the oxidizing? Copper. So the copper is being reduced, but it's also the thing that's causing zinc to be oxidized. So it is the agent that is causing the oxidizing. We call it the oxidizing agent. Is the thing that's being reduced, is it also the reducing agent? No. What's causing copper to be reduced in here? The zinc. The zinc is causing, this is causing, or it's forcing Cu2+ to be reduced. So the thing that's being oxidized is causing something else to be reduced. We call it the reducing agent. If something is being oxidized, it's the reducing agent. If something is being reduced, it's the oxidizing agent. Is that crystal clear to everybody?
Yes.
My intuition tells me that that's not crystal clear. This is a really screwed up concept. It's that they're totally opposite, but it's really easy to kind of misrepresent which thing is being the opposite of which thing. So we say that copper, because it's causing zinc to be oxidized, this is the oxidizing agent, and we say zinc is the reducing agent. Now, there's a really easy way to just discriminate between these two. And, what does our lion say? Leo the lion says grr, right? Okay. So, so now, the thing grr, the thing that's gaining electrons, the thing that's being reduced is also the oxidizing agent. So now we will amend our statement to say Garoa. That's what the line says. Garoa. How clear is that? Yeah. So from now on, I'm almost exclusively going to say just Garoa. Because what's the exact opposite of Garoa? Leo. So now instead of Leo the lion, we could say Leora the lion says Garoa, but that just doesn't, that doesn't really help anybody. So, yeah. Yeah. So we're going to stick pretty much exclusively with Garoa for now. And I put the slash in there because at the beginning of chapter 14, we're going to add another letter in here.
Oh, great.
What? No, it's not P. No, it's not Gerpoa. No, yeah.
Can you add that to that?
Can I add that to that? Oh, yeah, sure. Let's do that. Yeah. Is this all you look at, Jordy? Yeah, that's all you've been looking at for the last week and a half. Garoa and Liara. Perfect. So that's helpful. Good. All right. Nice talk. Okay, so let's identify the oxidizing and reducing agents in the reactions below. Remember, if something is the oxidizing agent, it's causing the other thing to be oxidized, right? So if something is the oxidizing agent, it's gaining the electrons that the thing being oxidized lost. So it's complicated, but we'll get used to it. Identify the oxidizing and reducing agents in the reactions below. Remember, either this or this will be the oxidizing or reducing agents, right? It's only these two things. It's not our products. It's what we have at the beginning. So iron. Is iron changing at all? What's it changing from and what's it changing to? It's changing from +3 all the way to 0. So is it gaining electrons or is it losing electrons? It's gaining electrons. And what do we say? Which one of these gains electrons? Does the oxidizing agent gain electrons or does the reducing agent? The oxidizing agent gains electrons and is being reduced. So now this is our oxidizing agent. What happens to the carbon in carbon monoxide? It goes from +2 to what? To +4. Are we okay with that? Carbon goes from +2 to +4. So is it gaining or losing electrons? It's losing electrons, and that means it's the reducing agent. Are we okay with that? I would like you to figure out what the oxidizing and reducing agents in the next two are. Okay, I'm hearing a little bit of chatter, so we'll do the second one and then we'll do the third one here. The magnesium, what's the oxidation number of the magnesium to start out with? 0. What's the oxidation number of the oxygen? 0. And then what is the oxidation numbers of the magnesium and the oxygen? +2 because the oxygen is -2. So what in here is the reducing agent? Is the magnesium the reducing agent? So the magnesium is losing electrons, and whatever loses electrons is the reducing agent. And the oxygen is gaining, so it must be the oxidizing agent. Does it make sense that oxygen would probably be the oxidizing agent sometimes? Yeah. Okay, good. All right, good talk. So, nickel, what's the oxidation state of the nickel here? +2, -2, 0, 0, +1, -2. So nickel's going from +2 to 0. That means it's gaining. Hydrogen is losing. So nickel is the oxidizing agent. Hydrogen is the reducing agent. Is that fairly clear? Yep, cool. So now you can all of a sudden, I'm not saying I want you to, but now all of a sudden you can answer a lot more questions in your assignment. So we can write up a lot of different reactions that maybe hypothetically could actually work, but in reality, only a certain number of reactions are what we call spontaneous. A spontaneous reaction is a reaction that naturally progresses. Like when I put one thing into another thing, you get a reaction. And I don't have to put in any energy. I don't have to put in any extra energy to let it go. So for example, when I have nickel ions and they come into contact with cobalt metal, I automatically, without having to put in any energy at all, the nickel ions will steal the electrons away from cobalt. So the nickel turns into a metal and the cobalt turns into an ion. This is because the electrons are more attracted to the nickel than they ever were to the cobalt. Do you agree cobalt, because it has an oxidation number of 0, it's got some electrons that it could give away if it wanted to? Would you agree with that? Because it's a metal, metals usually like to give away electrons. Nickel is +2, so it could accept some electrons. And it's all has to do with, are the electrons, are they in a lower energy position with the cobalt or with the nickel? So who's winning the tug of war here between the electrons? Do the nickel ions successfully steal the electrons away from the cobalt? Yes, because it's what we call a spontaneous reaction. And so let's take a look at a different case where zinc in here, zinc's 2+, cobalt's 0. It's kind of the same thing as before, right? But if I stick a chunk of cobalt into some zinc, does zinc successfully steal the electrons away from cobalt? No. Basically what's happening, we actually get no reaction. It's what we call a non-spontaneous reaction. Now the reaction could happen if we gave it a little bit of extra energy. But without any extra energy, the reaction does not occur. So we see no evidence for a reaction here. You stick the cobalt in some zinc ions and nothing happens. Jordy?
Sorry, what's the difference between the two reactions?
Well, the difference is, here we're taking cobalt, like a chunk of cobalt, and we're sticking it in some nickel ions, and the nickel ions will successfully steal the electrons away from the cobalt. But here we're taking cobalt and we're dipping it into a different solution full of zinc. And the zinc ions aren't strong enough to steal away the electrons from cobalt. So the cobalt metal will react with some ions, but it won't react with some other ions. And this is what we call either a spontaneous or a non-spontaneous reaction. You will see evidence of this reaction happening. You will not see any evidence of this reaction happening. And so later on, when we're doing kind of our review for this unit, I'll do a little demo and I'll kind of prove this to you. Just that our lab tech is really busy right now and she didn't have the time to be able to make one for me. And back. But what I have here, oh man, here we go. Here, so we're just gonna watch a video. It's pretty short, but we'll scooch to the part where we want to go to. I think this is good enough. So what's happening is we're gonna put some zinc into the copper sulfate. So this is a mixture of copper sulfate right now, and we're going to put the zinc into the copper sulfate. And we're going to see if we get a spontaneous reaction. And I just kind of want to show you what a spontaneous reaction looks like. So we've added some zinc powder to the bottom of the copper 2 sulfate. And we're just going to scooch ahead a little bit in time. And what do you notice is happening to the color of the copper 2 sulfate solution?
Attention Lindsay Thurber, this will be a practice of our hold and secure procedure. At this point in time, staff members responsible for hold and secure, please execute your responsibilities.
Okay, so a hold and secure. Yeah, sure. We'll pause the video. Okay, what do you notice after we added the zinc to this solution? What do you notice happened to the color of this solution?
Brown.
So it started, what color did the solution start out as? Like a pretty vibrant blue color, and as we go, what's happening to the solution?
Good morning, may I have your attention please, Lindsay Thurber. Currently our building is under a practice hold and...
Okay. So do we agree that we did see some sort of a spontaneous reaction? We didn't need any extra energy. We didn't need to add some electricity. We didn't need to heat it up or whatever. Do you agree that this reaction just kind of went very naturally and just worked the way it normally would? Are we okay with that? That's what a spontaneous reaction would look like. So we added some zinc metal to some copper ions, and the reaction proceeded. Okay. Now, there's a way for us to predict whether or not a reaction is spontaneous or non-spontaneous. So in the reactions above, nickel ions have a greater affinity, and affinity is just like a greater relationship or attraction. So it's a greater affinity for electrons than the cobalt. Because nickel has a greater affinity, we say it is a stronger oxidizing agent. So in here, the nickel has a greater affinity for the electrons, so it will steal cobalt's electrons. In the second example, zinc doesn't have as great an affinity as cobalt, so it can't. It's unable to steal the electrons. Does that kind of make sense? That something will have a greater affinity for electrons, and if it does, it's able to steal the electrons away from that other thing. Joe?
Is there any way for us to know?
Yes, there's a table in your data booklet that you'll already see on page 7. So you can either look at it, or I put in the notes. It's whatever. It's fine. It's in the notes right now. So this is our table of half reactions, right? Yeah, and so in here it has something to do with electron potential, but we're going to talk about that in the next chapter. This is how you would figure out the voltage of a battery or something like that. So we could have two half reactions, and we could figure out what the voltage for that battery could be, and we could predict whether a battery would be strong enough to do something or not do something. So in here, what we have is at the very top, let's look at this. Do we have, on the left-hand side, do we have lots of metal ions, or do we have lots of metal atoms? We've got lots of metal ions, maybe not way up at the top, but like gold ions, mercury ions, silver ions, iron ions, blah, 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 blah. On the right-hand side, do we have lots of metal ions or atoms? We've got lots of metal atoms. So over here, on this side, on the left-hand side, we've got oxidizing agents. How do you know on the left-hand side there are oxidizing agents? Because they're all reduction half reactions. Every single one of these is gaining electrons. And when you gain electrons, are you the reduction Yeah, reducing agent or the oxidizing agent? The oxidizing. Okay, good. So up at the top here we have the strongest oxidizing agent that we can really have is fluorine gas. And way down at the bottom, we've got the weakest oxidizing agent we can really have. Whoa. So what's the strongest oxidizing agent? What's the thing that really wants electrons more than anything else? Fluorine. Does that make sense with what you know about fluorine? Fluorine is extremely reactive. It has the highest electronegativity out of any atom. So it generally has a strong affinity. Over here, what we have is we have the weakest reducing agent. Are you seeing anything in common with a different table that we've used? The acids and bases, right? So we've got our strongest oxidizing agent up at the top here. Where's the strongest reducing agent? At the bottom on the other side. So this lithium atom, that's our strongest reducing agent we can really honestly have. Lithium atoms are pretty much the strongest reducing agents. That's why lithium-ion batteries are used, is because they're turning lithium into lithium ions, and that's a really strong reducing agent, right? Yeah. Okay. So I'm going to scooch back and forth. But you can predict whether or not something is spontaneous or non-spontaneous. You can predict that using your table. What do you notice about this and this? It's uphill and downhill again, isn't it? Yeah, not again. Okay. In the equilibrium unit, when we were doing, calm down. Yeah, I know it's cartoon characters. Just calm down. In the equilibrium unit, when something was downhill, that meant it was products favored. Now, yeah, Toad's dead. Calm down. Yeah, no, I'm not joking. Toad is the weakest character.
That is so true.
What about Yoshi's way stronger than Toad? But
What about Bowser though?
shut up, let's figure it out together. Yeah, let's figure it out as a group, please. No, calm down. I'm sorry, Jonas. Samus. Yes. I mean, we can call her Samus if you want. Yeah. Let's call her Samus. Okay. We'll go through it.
You did him dirty.
Okay. Actually, shut up though. Let's try this. Whenever you have a downhill reaction, you will get a spontaneous reaction. Whenever you have an uphill reaction, you will get a non-spontaneous reaction. Now, that doesn't mean non-spontaneous reactions can never go forward. It just means we need to do something to force that reaction to go forward. When building a table, create a rough copy of the table beside the question. If we're building a redox table, always write the oxidizing agent. So for example, I just want to go back. And I want to take a look at this. Let's talk about the reaction, Jonas. Stop. Let's talk about the reaction that we saw earlier. Let's take copper 2 ions and react them with nickel metal. I want you to tell me, first of all, did we see in the video, was this spontaneous or non-spontaneous? In the video, when we added the zinc to the blue, and then we saw the blue go away, that's a spontaneous reaction. I want you to prove to yourself I want you to find copper ions and nickel metal. Sorry, it was actually zinc, but I don't think it's going to matter. It was zinc that we used. Does this combination, does it make a downhill or an uphill reaction?
Both of them.
So where are copper 2 ions? Are copper 2 ions on the left-hand side or the right-hand side?
Third and a half man.
Did you say a third and a half?
Yeah, damn.
Copper ions should be here. Good. Okay. Yeah, there is 2 copper ions, isn't there, right?
Yeah.
But what? Okay, calm down. So there's copper 2 plus over here. Do you agree copper would be acting as an oxidizing agent? Because it would steal the electrons. Okay, where's zinc? Zinc's on the right-hand side and it's way down here. So copper was way up there. Is this an uphill or a downhill reaction? It's downhill, so this is spontaneous. So hopefully that makes sense. That yes, that's spontaneous. What we want to do, we want to build a redox table, just like you have in your data booklet. Now we're going to make an analogy, yes, calm down, to video game characters. Okay. Remember, there's a battle in these redox reactions. It's basically a tug of war for electrons. Something is trying to steal something else's electrons. It can either be successful at stealing the electrons or unsuccessful at stealing the electrons. And so what we're going to do is we're going to put the entity that is successful at stealing the electrons, we're going to put them on top. Does that make sense? If they win the battle for the electrons, we will put them higher than the loser. Is that okay? So a lot like video game characters, where we could rank these video game characters for who would beat which character. So let's try this. A couple comments. Have like a little rough copy going on the side, and then once you have all of the once you have all of the battles kind of roughed in, then you can make a good copy. So what we're going to do is we're going to make a rough copy, and then on the bottom we're going to make a good copy. And be prepared to cross things out or erase things or whatever. So let's try and think about this. Samus versus Yoshi. Who wins? Samus. So what we're going to do is we're going to put Samus above Yoshi, but give yourself a little bit of space, because we don't know if Yoshi is the second best player in this tournament or whatever. So, Mario and Toad, who wins? Mario. So off to the side, I'll say, okay, I don't know who wins between these people, but I know Mario beats out Toad. And unless we're talking about Mario Kart, Toad sucks all the time. That's okay. Deal with it. Yoshi versus Toad, who wins? Yoshi. So where would we, in like the rough copy, where would we put Toad?
Below Yoshi.
Below Yoshi. So I'd put a little bit of room here. Right? Just give yourself a little bit of room. Do we know where to put Mario yet? Should Mario go in between Samus and Yoshi, or Yoshi and Toad, or do we not know yet?
Mario. Well, Samus kills Mario.
So,
Shouldn't Mario go in the top though?
Guys, name Mario.
Yeah,
so
it's Samus.
yeah, who beats Mario? So we know. I knew this was going to be a nightmare. Okay. Do we know where Mario goes? We know Mario is below Samus, right? Okay, so I'm gonna rewrite Mario over here because we know Mario has to go below Samus. We're not totally sure yet. Okay, Mega Man and Samus, who wins?
A close fight.
It's a close fight. So no, Samus is always gonna win. So because we know Mega Man is so close to Samus, let's put Mega Man just below Samus.
But you only get one fight.
Yeah, I know. I understand that. This is just an analogy. Calm down.
He's fought so many people. He's probably
And we can
Toad is probably dead to us.
And then Mario versus Yoshi. Who wins?
Yoshi's dead.
Yoshi's dead. So, we've got Yoshi. Should we put Mario on top or below?
On top.
We should put Mario on top. So what we can do is we can take this and we can kind of make a good copy. So Samus is the strongest, and then Mega Man, and then Mario, and then Yoshi, and then finally
Toad.
poor old sad Toad. Deal with it. Toad's not perfect. Toad's not perfect. Hey, let's try this. What can you say? What can you say about? Let's try and pick two of these people that didn't fight in the tournament, and let's try and see if we could figure out whether or not they would, one person would win or one person would lose. Did Samus ever battle Toad? No. But what can you say?
Toad's always dead.
What can you say about the interaction between Samus and Toad?
Toad would die.
That Toad would be obliterated,
Yeah.
right? Absolutely. What can we say? What can we say about the interaction? What can we say about the interaction between Mega Man and Mario?
A close fight. Talk about Mega Man.
Yeah, Mega Man would win against Mario. That's the idea behind this. Okay, so this is the way normal redox tables are made. Yes, this is like a bigger ice table, except it's way more simple.
Oh, okay.
What we have going on here, and this is the demonstration that I'm going to provide for you later on, but what we have going on here is we've got copper metal interacting with copper ions. And what we want to know is who's going to be stronger, copper or copper? Well, in this case, there's no way to really tell, so we say it's a non-spontaneous reaction. Same as zinc and zinc, same as lead and lead, and same as silver and silver. We say that they're non-spontaneous reactions.
This is looking like a badminton tournament.
It very like bracket, 100% it is. And so what we want to do at the end of the day is we want to rank the strongest oxidizing agent at the top, and we want to rank the strongest reducing agent at the bottom. That's our goal for this. So let's try this out. When we put copper 2 ions and zinc together, do you remember, was this copper 2 ions, the blue water, and the zinc metal, was that spontaneous?
Yeah.
Yes, absolutely that was. It turns out that copper 2 ions will react with lead, but they won't react with silver.
Are you getting that?
I'm not getting it from the table. I'm getting this based off of just personal experience. Again, I wanted to do this demonstration in front of you, but our lab tech was too busy. We'll just do it as a review later on, okay? Now, when I put zinc ions on copper, we don't get a reaction. When I put zinc ions on lead, we don't get a reaction. And when I put zinc ions on silver, we don't get a reaction. The zinc ions are pretty bad, aren't they? Yeah. when I put lead ions on copper, we don't get a reaction, but we do get a reaction with zinc, and we don't get a reaction with silver. And when I put silver ions on all three of these metals, we get reactions on all three of these metals. So let's think about this. Who steals the most electrons? Which oxidizing agent here steals the most electrons?
No, it doesn't.
So what I want to point you towards is that our metal ions are all up here. These are all the oxidizing agents. And over here, these are all reducing agents. The metals have electrons to give up, right? The metals have electrons to lose, so they're the reducing agents. The ions have electrons to gain, and they're oxidizing agents. Alicia?
So why doesn't the lead ion react with the copper metal with copper and lead?
Okay, that's a great question. So the lead ion does not react with the copper metal, but the copper ion does react with the lead metal. Why is that? Which one of these elements do you think is more strongly attracting the electrons? Who's winning the battle for the electrons? Are the copper ions, Alicia, are they successfully stealing electrons away from the lead? Yes. So if copper is winning against lead, does it make sense that lead will not win against copper? Does that make sense? They're like two opposite kind of reactions. Okay, which oxidizing agent is the strongest? Which metal ion wins the most battles? Silver. So what I'm going to do is I'm going to put silver on top. This is my strongest oxidizing agent. But it's also my weakest. The silver metal is my weakest reducing agent. Then what's my next strongest oxidizing agent?
Copper ion.
When I look, the silver ions win 3 battles. What's the next strongest oxidizing agent? The copper. So where would we put copper? Would we put copper above or below the silver? We'll put it below. Because in the interaction between silver and copper, silver wins the battle for the electrons. Kelton. Yep. Yeah, next.
Are we just basing that off like the stuff that are in the left column? So like if you threw stuff in the left column, is it possible to like for silver to be the best and like something else to be better than silver?
Yeah, it's totally possible. Like if we added a 5th metal here, let's say we added gold. Gold is a stronger attractor of electrons than silver or any of these other metals. So if we added a 5th column and a 5th row to this, then gold would be the highest, but we didn't have gold, so silver right now is our strongest oxidizer. Yeah. Okay, so what's the next strongest oxidizing agent in here? It looks like lead, the lead 2 ions. And all I'm doing is I'm completing the redox half reaction. That's all I'm doing. So I'm saying lead 2 plus ions plus 2 electrons turns into lead sulfur. And then finally, what's our weakest oxidizing agent here? What's the one thing, the oxidizing agent that never reacts with anything? Zinc. So zinc and really I should put the states of matter in here because they are aqueous. So here's going to be our weakest oxidizing agent. But what do you notice what do you notice about the reducing agent that's kind of the opposite of the weakest oxidizing agent, if that makes sense? What do you notice about the zinc metal? It was the strongest reducing agent, right? It was the metal, the solid metal atom that reacted with the most things. So this is how a table is created. This is our strongest reducing agent. Basically, the way we made that table was we had to do a bunch of different reactions, and we had to see who's winning the battle for the electrons. If they win the battle for the electrons, we put them on top. If they lose the battle for the electrons, we put them on the bottom. And then we keep inserting things wherever they win or lose. Does this kind of make sense? Yeah, the table is really nice. You're not super likely to get a table on the diploma exam. You're more likely to get what we're about to see, the next example. How many reactions were in this table? How many X's and check marks? 16. 16 reactions. We could figure out the exact same thing as long as we had 4 reactions. That would help us. That would be able to, that would let us do the exact same thing. But we'd have to pick 4 very specific reactions. So in here, we're going to build a redox table. It's going to be the exact same thing as what we did before. Whoever wins the electrons, we put on top. Whoever loses the electrons, we put on the bottom. Are we okay with this? We're going to get a rough table going, and then we'll make a good copy of the table off to the side. Okay, so cobalt ions and indium. Are the cobalt ions successful in stealing the electrons away from indium? Yes, so what should we put on top? We should put cobalt on top. So that's what I'm going to do. I'm going to put my oxidizing agent on top, the cobalt 2+. Now, I understand people want to put indium solid down below it, but they shouldn't. They should put the oxidizing agent version of indium. Which one of these 2 indiums is the oxidizing agent version of it? The indium ion. So we'll put the indium ion below the cobalt. Does that kind of make sense? We need to have all our oxidizing agents on the one side, and we need to have all our reducing agents on the other side. Okay, well, let's look at the next reaction. Does copper successfully steal the electrons away from cobalt? Do we see a reaction here? Yeah, we do. So copper is successful in stealing the electrons away from cobalt, so we'll put copper where? Should we put copper above or below cobalt? Above. It wins the battle for the electrons. So we'll put copper 2+ above. And then let's try copper 2+ and palladium. Is copper 2+ strong enough to steal the electrons away from palladium? No. No, it's not. So where should we put palladium? Should we put palladium above or below copper? This is the hardest part about this. Who is actually winning this battle for the electrons? Palladium.
Physical development.
Yes, that's okay. So where would we put palladium, above or below copper? We would put it above, okay? But palladium solid would go on the other side, right? It would go on the right-hand side, because this would make a downhill reaction. So what's the ion version of palladium? Does anybody know?
Palladium.
Yeah. Palladium what charge? It's probably going to be 2+, because that's the most common ion charge, right? So, our good copy of the table would read like this. We have palladium ions on top, then copper ions, then cobalt ions, then indium. So we would have palladium ions on top, then copper ions, then cobalt ions, then indium. And this is where people stop paying attention. They say, oh, we've got half the table, we've got our oxidizing agents, that's awesome. But let's finish the table. Why am I putting 2 electrons, 2 electrons, 2 electrons, and 3 electrons? I'm trying to balance out the charges, and I'm trying to make the metal, the solid metal version of it.
Wouldn't it be equilibrium arrows?
Yeah, you totally 100% could put equilibrium arrows. 100%, yep. And I probably should be using equilibrium arrows.
Okay.
But I just developed the habit of writing half reactions with straight arrows,
Okay.
quantitative arrows. Okay, perfect. What's my strongest oxidizing agent in here? Where do you see the strongest oxidizing agent?
Top left.
Top left. So what's the strongest oxidizing agent here? Palladium 2+. This is my strongest oxidizing agent. What's my weakest oxidizing agent in here? The indium. What's the strongest reducing agent in here? The indium metal. And what's the weakest reducing agent in here? The palladium metal. Okay, let me ask you, I just want to double check some stuff. Let's double check and see if our table was correct. That first reaction that we had cobalt ions with indium, was it spontaneous? Did you see a reaction? Yes. Find cobalt ions and find indium on our table. Not on your table, on our table. Do the cobalt ions and the indium, do they make a downhill reaction? Good, so that reaction is fine, right? What about copper 2 ions and cobalt? Find copper 2 ions and cobalt. Here and here, is that downhill? Yes, that's good. And then find copper 2 ions and palladium. Was that uphill? Yes, good. Then our table makes perfect sense and we were happy with this. What if I chose cobalt ions and palladium metal? What if I chose cobalt ions and palladium metal? What would happen? Nothing, because that's an uphill reaction, right? These are all the kinds of things that the diploma could ask you. The diploma could ask you, it could give you these 3 reactions, and then it could say, well, what if you had this reaction? You would have to build a redox table and then try and identify whether or not it's uphill or downhill to figure out if it's spontaneous or not. I totally recognize that this is like the blurriest screen capture in the entire history of the world, and I understand that. But what I would like you to do is I would like you to build a redox table, and it's asking you when the oxidizing agents are arranged from strongest to weakest, right? Top to bottom, what order are they in? So do the exact same thing we just did. Ask yourself, is this ion stealing the electrons away from the atom? Go ahead and try and build a redox table. If it wins, put it on top. If it doesn't win, put it on the bottom.
was working, that's why.
And Sunday
Yeah, that's because it was asking about oxidizing agents, right? But if it was asking about reducing agents, then you'd have to fill the whole table.
Sometimes just close it.
Up on the right.
Oh, that's you, okay.
Yeah. I agree. It doesn't have to be hard, but it can be hard. And the reason why it starts to get really hard is if we ever have if we ever have questions that ask using like if we start putting in non-metals in here, then you get really screwed up. It's kind of the same except I just want to talk about it. Yeah, you can work on it.
I don't know why I got set.
Okay, I'm gonna do this pretty quick. So if you have any questions, I would like you to shout at me and let me know so we can discuss it. And remember, if you have a question, you are probably not the only person who has a question. Okay. We always want to stack our oxidizing agents on the left-hand side, and we want to put our reducing agents on the right-hand side. So S2 plus, does it successfully steal the electrons away from T? Yes, so I'll put S2 plus above, I'm not going to put T, I'm going to put T positive, right? Because that's the oxidizing agent version of T, whatever T is. I was going to call it tellurium, but it's not. Okay, R3 positive. Does R3 positive successfully steal the electrons away from T? No, so where should we put R? Above or below T? Below T. R3 positive. Then we've got R3 positive and V. Does R3 positive successfully steal the electrons away from V? It sure looks like there's evidence that it did successfully steal it. So we'll put R3 positive where? Above or below V? Above V, so that means V2 positive has to be here. Now, here's my oxidizing agents, and on the other side of the arrows would be the reducing agents. What's it asking us for, the oxidizing agents or the reducing agents? So we don't even have to really complete the table, do we? What's the strongest oxidizing agent in this list? S2 plus, and the only thing that starts with S2 plus is A. That's our strongest oxidizing agent. All right, does that make sense? Are we okay with that? So, on the next question, what I would like you to do on the next question is I would like you to rank these from weakest reducing agent to strongest reducing agent. And you need to put their actual reducing agents in here, not the oxidizing agents. Let me know if you have no idea what we're doing, or if you're lost, or if you have any questions. Yes.
No.
No, I mean these. Yeah.
If no one's there,
But I agree, Kelton. I'd agree.
S would be the weakest. Okay, so that makes sense. So then wait, so then what? We just apply it to Julie. So then you gotta write it. Well, he should. I mean,
Yeah, Denver, say sorry.
it wasn't me. It wasn't.
Oh,
it
but
wasn't
you're
my
not
fault.
doing your work, so say
I know.
sorry.
I'm sorry.
Okay. Nah, just get to work.
Yeah, God.
I had to finish my conversation.
Okay, so which one of these, like, which one of these could act as a which one of these could act as like cadmium?
Oh, the second one is because he slept in.
Good. So I can put O and
Well, no, because it's because he got sick, right? So you can't call him sick, which is okay.
yeah. So which one of these is more successful?
So you're welcome.
And at the end of the day, who has the electron? Does the cadmium electrons?
Yeah, so
He's not even.
The cadmium wins the electrons.
they're on his line.
Right, so who should go higher?
As soon as he gets
Cadmium, right? Now, if you want to force oxidizing, 65. What's going to go for those?
It's not the whole thing.
it's not real loud. I don't know why that experience is so away from myself. Like you could say that, yeah, but you could like I can't.
Okay, so let's go to the next one. Well,
Like he should have.
cadmium.
What do you mean you're not saying?
Yes.
Did he get cut in?
Do you have a backup job though?
I mean, he wants to work at something good.
You almost yelled at. No, that's bad.
So what?
Okay. Yeah. What? Oh yeah, sorry. There are 5 things. So I apologize. Alright.
I never applied.
So let's do this question. There's 3 minutes left in class. Yeah. Hey, who wins the battle for the electrons, cadmium or beryllium? Shh. Who wins the battle for the electrons, the cadmium or the beryllium? The cadmium. The cadmium ends up with the electrons, right? So I'll put cadmium 2+ above beryllium 2+. And who wins the battle for the electrons, the hydrogen ions or the cadmium? It looks like the hydrogen ions successfully steal the electrons away, right? So I'll put the hydrogen ions above. Now what about calcium and beryllium? Who's kind of winning this battle? Does beryllium give up the electrons or does beryllium keep them? Keep them. So who needs to be higher, beryllium or calcium? Okay, so beryllium, and I'll put, I don't know how far down, but I'll put calcium. Oh. And then copper or hydrogen? Copper retains the electrons, right? So it wins. So copper needs to go way above, right? So I'll make my good copy of a table. Copper 2+, hydrogen plus, cadmium beryllium, and then finally calcium. Now, are these reducing agents or oxidizing agents? Oxidizing agents. So we could turn them into reducing agents. So copper metal, hydrogen gas, cadmium metal, beryllium, and calcium metal. Where's your strongest reducing agent? At the bottom, right? So calcium, then beryllium, then cadmium, then hydrogen, and then finally copper. Why did I not put any charges? Because all of these are atoms.